Okay, so welcome back everyone to the FOL Methods for Software Engineering lecture. And today we're starting a new topic. So the last lecture didn't happen because of the holiday, but today we're starting a new thing, and that's called satisfiability modular theory. So as you remember, we have those kind of 4 chapters. We completed now the SAT solving, but we're still working on the homework. Some of you, I'm not sure, did anybody already submit the homework? No? Okay, so that's yeah, I think next week, due next week, right? Friday next week or something like that. Yeah, great. Yeah, so today we'll start a new topic, and we will look at what we have learned so far. We have learned SAT solving, and we know what SAT solving is based on, what kind of language we can use, what logic we can use to express our problems, and we can express them in this propositional logic. Yeah, in this logic, propositional logic, where we have variables that are just atomic propositions or Boolean variables that can be true or false. And there might be things that we cannot easily encode in as a SAT problem because we cannot easily express them in propositional logic. So can you give maybe some examples of what could it be that we cannot yet handle? So this lecture doesn't stop with SAT solving, it continues, right? So what is it that might be missing? Does anybody remember things that we can express in SAT? We had these like natural language descriptions that we could translate to, well, statements, logical statements that we could translate and then check whether one statement follows from other statements, right? That's something we could do. Then role-based access control, we could check parts of it, right? Feature models, we could analyze them using SAT. So here are some examples. Well, we have one example. Why we are here. Yeah, that's difficult to encode in SAT. Why is that? So yeah. Why is it difficult to encode? I mean, in general, all these tools that we're looking at, a why is very difficult, right? So maybe we would have to concretize this here or something like that, right? But even if we have a question of, let's say, why can I not include this product in or this feature in my product? This is a separate story, and there are works on the why question of formal analysis. They probably will still not answer why we're here, but yeah. And I'm afraid that also the other tools that we're going to go through, they will not be able to answer this question. Any more things we cannot express in SAT, or we cannot easily express in SAT. Okay, so let's look at some examples and see if we can encode them in SAT. If SAT is so powerful, maybe we can encode them. So here is a logic puzzle. It's just logic, so we should be able. It's similar to this. What was his name? Was it Paul who missed the train? Was it Tony? Who was it? At the train station, and there were no taxis at the train station. Then he might be late for his meeting. Hmm? John. I was John. Yeah. Okay. So John is not in this, but there are other people in this. So here we have the Dreadberry Mansion mystery. Someone who lived in Dreadberry Mansion killed Aunt Agatha. and Agatha, the butler, and Charles were the only people who lived in Dreadberry Mansion. A killer always hates their victim. So we have a bunch of statements about some people, right? We have only 3 people, Agatha, the butler, and Charles. Then a killer always hates their victim and is never richer than their victim. So it's a made-up setting, but you could see that it involves some maybe relations between people, right? So there are some maybe special things like killer. So this is probably maybe one of those, if those were the only ones there, right? Maybe one of them is the one who killed Aunt Agatha. And then there are some more information we know about these people. So Charles hates no one that Aunt Agatha hates. So there's some relation again between Charles and Aunt Agatha. Agatha hates everyone except the butler. The butler hates everyone not richer than Aunt Agatha. The butler also hates everyone Agatha hates. No one hates everyone, and Agatha is not the butler. So who killed Aunt Agatha? Okay, let's encode this in SAT. How would you encode this in SAT? So if we think back at other encodings that we did, right? We had the encoding of the role-based access. We had the encoding of the feature models. The first thing we had to think about is what are the variables. So in the role-based access, we said that the variables might be the roles and the capabilities, or well, maybe just so which role do you have and what capabilities then should you have, and then we wrote some predicates around these. In the feature models, we decided that the features will be the variables because they're either there or not there, either included or not included. So what would be the variables in this puzzle now? Okay, so you could consider okay, but this okay, so I think we can maybe ignore this, that Agatha is not the butler. We can also say that Charles is not the butler. Let's say those are really 3 separate people. Agatha, the butler, and Charles, they're all separate people. This is a bit stronger than this last or the previous to last point here, which just says that Agatha is not the butler. Let's say the butler is its own person. So then this makes it slightly simpler. Yeah, but how do we encode stuff like who's richer? If you have richer as variables, according
to the third statement, Aunt Agatha was the richest.
Okay.
Because she died, and the victims must be poorer than her to kill her, or at least she's richer than the one who killed her.
Yeah. Okay, but how do we express that she's richer than the one who killed her if we only have Boolean variables? So actually the information that we know is true is a bit more composed of multiple things, right? It's not only that someone is richer than someone else. We know that some killer is never richer than their victim, so we have to relate killer and victim in this kind of richer thing. So how many combinations could we have when we have Agatha, the butler, and Charles? We have 3 people, so we could probably relate 3 people each to each. So it's 9 possible combinations. So we have 9 Boolean variables for who is richer than who else. So we could have a Boolean variable saying Agatha is richer than Agatha. We could have one that says Agatha is richer than the butler. We could have one, Agatha is richer than Charles, right? So for this richer, we would need then, well, 9 variables. For hating, how many do we need? Again, 9 variables, right? Because that's again a relation between people. And we know something about these variables, right? So we know Agatha hates everyone except the butler. So we know that some of these variables are true, some are false. And we can write this down as constraints. Do we have other things that we need to express in variables? So we have 9 variables for richer, 9 variables for hating. Do we have other things that we would need to express in variables? How do we reason about
Being a killer.
being the killer? Yeah.
Agatha is not the killer because she died.
So how do we relate being the killer? How many people could be the killer?
3.
3 again. So we have because that's now what's the difference between hating and being the killer? Why do we only need 3 variables for being the killer and 9 variables for encoding hating?
He can either be a killer or not.
Okay, yeah, because every person can be a killer or not, but it only relates to a single person, right? Hating relates to 2 people. So that's the big difference, that we have some kind of things that relate multiple people, and then we kind of blow up the variables because it's the number of people times the number of people. If we would have something that relates to 3 people, 3 people, then it would be 3 times 3 times 3. So we would already have 27 Boolean variables. So yeah. Now, how many other relation? We had the hates relation, we had the richer relation, we had the killed relation. That's maybe it. Don't know. And then we have a lot of constraints that we have to write, right? Each one of those we have to encode. Okay. Yeah, that's maybe a possibility, but maybe not the nicest one, right? We have one answer. Is that somebody who didn't answer? Okay, assigning the roles and expressing the dependency and solve. So we basically, these roles, like whether somebody is, the roles or maybe the relations between the people, right? And then the dependencies are maybe the constraints that we know. So we could probably encode this in SAT, but it would mean we have a lot of variables and we probably have quite a few constraints on these variables. Okay, and well, after this encoding in these variables, how do we know who killed Agatha? We check satisfiability. We get, hopefully, a solution, an assignment. And this assignment gives us what?
Killer is equals to 1. It satisfies 1.
Well, we have 3 variables for killer. We have, like, Agatha is the killer, Butler is the killer, Charles is the killer. So, well, one of them or many of them might be true. But actually, there's something we overlooked. Because that they are the killer doesn't mean they killed Agatha, or does it mean, well, I mean, here it says that, wait, someone who lived there killed Agatha. Maybe more people are dead, I don't know. So actually, I would say that killed is again a relation between 2 people. Well, yeah, 2 probably, yeah, or more. 2, I guess, would be fine. So we would have even more variables. So maybe SAT is not the best, unless you do it completely programmatically and you don't care how many variables you generate. But doing this manually, it's probably not the closest. And why is that? What's the problem there? Why do we need so many variables?
So many possibilities are there.
There are so many possibilities, yes. And so it's a bit like, if you think about, did anybody ever write assembly code or machine level code? You need many, many lines to express some things that in, let's say, some high level programming language, you can express much easier. So, and the reason is that maybe some high level concepts are missing in this kind of assembly language. And I would maybe say that SAT is like our assembly language. It has very basic concepts. It has this concept of Boolean variables. It has, well, propositional operators on them and or stuff like that. But it doesn't have many high-level concepts. It doesn't have the concept, for example, of a relation or a predicate between. So this hates would be some high-level concept. Could be some high-level concept. But SAT doesn't really have that. So maybe we need some other language. And this is an encoding that might make it easier. So this is an encoding in first order logic, and we will look at what is this first order logic. So you can have a look at this. This is the translation of this puzzle. And now we actually have these kind of predicates here. We say there's a predicate killed that relates some person X to some person A, and this A would be Agatha. And we say there exists some X where X killed Agatha, right? And then we have the other ones. We have the hates relation and the richer relation. So yeah, for example, here it would say that Agatha hates Agatha and Agatha hates Charles. So this is because here it said Agatha hates everyone except the butler, right? So we will not have hates AB because Agatha doesn't hate the butler, but we will have the other ones there. Okay, so this is something, if we could express it in a language which is much closer to the actual way that the problem is formulated, this might be nice. So then what about this one? That's also maybe something you have come across, some puzzle about dogs, cats, and mice. So you can spend exactly $100 and you have to buy exactly 100 animals. Dogs will cost you $15 each, cats will cost $1, and mice will cost 25 cents. So if you have to spend $100 and you have to buy 100 animals, what would be the most simple solution here? You can't buy 100 dogs, right? Because that's too much money. You could buy 100 cats, right? That's each cat $1, that would fit. But it says here, you also have to buy at least one of each. So now that gets a bit more tricky. And then how many of each should you buy? Yeah. Anybody has an idea how many of each we should buy? How do we solve this in general? I mean, we could change the numbers, right? And it would be a different puzzle. So who knows this kind of stuff from school? Sorry? Okay, so you can basically put some arithmetic, some mathematical formulas on numbers. So you could introduce some symbols here. What is this dog, cat, and mouse thing here? Well, what does it stand for? It says, so that's basically, we have to buy at least one dog, at least one cat, at least one mouse. So this variable, dog, now is a number. And we say this number is the number of dogs that we're going to buy, and this has to be greater or equal to 1. So we have to buy at least one dog, one cat, one mouse. And then here we can use this same variable, but now we can add them up, and we say it has to be exactly 100 animals, right? And then here we just give the price in cents instead of dollars. So a dog would cost us, well, 1,500 cents, which is the $15. And the mouse would only be 25 cents. And all of them together, they should equal our budget of $100, right? So now all we have to do is we have to find some solution. And what would this solution look like? I mean, just in general, it would, like, what are we asking for here? We're asking for how many of each do we buy? So a solution would basically assign a number to each of these, right? Probably we want an integer number, right? We don't want to buy half a dog, right? So it would probably put some integer number to each of these variables, and this would be a solution. Now, how would we do this in SAT? Doesn't sound like it's a good idea to encode this in SAT, right? Because, yeah, what is missing in SAT about this? Variables in SAT were all Boolean. Here we want integers. Then what were the operators that we had in SAT? We had conjunction, disjunction, stuff like that. But here we have plus and multiplication. So we have addition, multiplication. All of these, that's all not in SAT, right? It makes things more challenging. What about puzzles like this? Who has ever seen similar puzzles like that? Yeah, so it's basically these symbols here, they are kind of variables. Yeah, actually, when we looked at this puzzle last time, it occurred to, I don't know, maybe one of the students that there might be some tricky meaning here, because this is a rainbow, right? The question is this a double rainbow, which is its own variable? Or is this 2 times this thing, which means we're actually only having the rainbow variable, the rain variable, and the, I don't know, lightning variable? Or do we have the double rainbow variable, right? So these puzzles, they're always not very clear, but that's a different challenge, right? But still, in SAT, that's probably not so easy, right? We probably want, again, some integer variables, and then we have operations between these. We have division, multiplication, and so on. And we have some equalities here. Like in the previous example, we also had these equalities here to say how many it has to be in total. So we want something that also can handle math, right? At least some kind of math. So now let's look at the second language that we're going to have. But I'm going to warn you, because this is really, we're going to build this up in a very, very formal way, because there are many things that are in this language. And very far on the bottom somewhere, there is basically propositional logic. And then there's stuff on top of it, on top of it, on top of it. And we will see that this is an extremely flexible framework that we're going to look at. So first order logic can be very complicated. We're going to look at it from a formal side. And then once we have done this formal side, we're going to look at it from, again, the, let's say, user perspective. So how are we going to use it to actually encode our problems in this kind of language? So it is important to have this background of this formal stuff, to know what is going on behind the scenes, so that we can see where are the challenges when we're trying to solve problems, or when we're trying to translate problems to this language. Why might it fail? Which are the cases that might work well? So again, as with SAT, this thing is not all powerful. It can't do all the things we would like it to do. The things that we saw on the slides, those it can do, those examples. But there is stuff where it is not that, well, not working so well. So we're going to look at maybe why that is, or what might be the limitations. Yes?
Every problems that we are seeing here can be done by programming, then why it's necessary to use a formal methods for solving?
So if you, how would you program these? You would maybe iterate through the possible solutions, or how would you solve this using programming? So like a search problem, right? Many of these tools, they actually can be translated to search problems. And what they do is they have been optimized and made very efficient to deal with this kind of stuff for, well, maybe decades that people have been working on this. So the thing is that if you translate your problem to SMT, and it is really as difficult as SMT, then the SMT solver will very likely be much faster than any of the programs that you write. But a very good observation is, if you can do it maybe with a simple algorithm, you should do it with a simple algorithm. So that's also what some colleagues are complaining about now, that they have to look at some works that people did, and people used SMT solvers, and they said, well, don't use SMT solvers in this setting. Because yes, SMT solvers are nice, but they're not the solution to everything. If you have something that works very, very efficient as a normal program, write a normal program, right? But if you have something that is very tricky, you don't know a solution, you don't have an existing algorithm, or the complexity of the problem itself is very high, the same complexity as SMT solvers, then probably they will outperform everything that you could write. But yeah, if your problem is not really a complex problem, then try to solve it in another way. That's the same with deep learning. Now everybody, like there's a hype in deep learning, everybody tries to solve everything with deep learning, even stuff they shouldn't, even stuff where there's other more simpler, straightforward solutions, but well, deep learning is great, so let's throw deep learning at everything. And yeah, don't make this mistake in general, and also don't make it with formal methods. So you always have to check, is this problem really a problem that pays off to translate to a formal method or not? And if it exactly fits the formal method, then you can imagine that probably the formal method has a much better, like faster algorithm implemented than you could write from scratch. Okay, so yeah. And we will see in particular for for SAT solving, if you have something where you have to try all the combinations, that's basically 2 to the n, where n is this number of variables. And I think that some people they measured empirically what is the real like expected complexity of SAT solvers, and in the worst case, of course, it's this 2 to the n. But they said I think it's getting close to like 1.2 to the n in practical cases. So that's like a much better thing, but still it has this high complexity. So yeah. And here we will see in SMT solving, we will see that there are basically many add-ons. So this stuff is arithmetic. And arithmetic can be solved very efficient using some specific algorithms. And actually, SMT solvers, they will do that. We will see what this T stands for, that it stands for theories. So SMT is basically, S stands for satisfiability. So that's like SAT. Then modulo, theories, means that we can incorporate some theories and also solve theories on the way that we're solving the SAT problem. And these theories, they have their dedicated solvers. So if you have something like with simple arithmetic, it will use an arithmetic solver in the background. So it will actually have a whole toolbox of solvers, and we call this thing all SMT solver. But the SMT solver will actually try to understand, okay, what's this component of the problem that you're trying to solve, and then try to use the dedicated solver for that. So yeah, there is a lot of engineering work in these tools. So yeah, let's have a look. The first, so this first order logic is our second language that we're looking at. The first was this propositional logic. Now it's first order logic, and we already saw that there is some additional stuff going on. So what we introduced are some functions, some variables, and some predicates. So predicates are sometimes a bit maybe not so obvious. So equals could actually be seen as a predicate because it has 2 parameters. Maybe on the left side, dog plus cat plus something is the left parameter, and then on the right side we have the 100, and this predicate is true if and only if left side is 100 and right side is 100, right? If they are really equal. Then based on these, we can build some atomic formulas or literals. If you remember, we also had something called literals in SAT. Our literals in SAT were very simple. They were basically an atomic variable, so an atomic formula like a or B or Q or R, and their negation. Those were our literals. When we talked about conjunctive normal form, we said that we can basically, on the innermost thing, we only have a variable or its negation. Those were our literals. Here, literals are already a bit more complex, but they're always wrapped into predicates. So it evaluates to true or false. Internally, it can use functions and apply them to variables, because that's basically what these predicates kind of wrap around. But then basically everything that kind of is wrapped in a predicate, that's a literal now. So everything that's true or false, that's inside some predicate, it's a literal now. Then we have some quantifier-free formulas, and we have formulas which have quantifiers. So basically everything without those quantifiers, that's a quantifier-free formula. And the quantifiers that we usually have, they are this for all and exists quantifiers. So here we only see the for all quantifiers, but we will go a lot more in detail of how to build up our logic. So these functions and variables and predicates, they're not arbitrary. We have to kind of define them for our language. So for function symbols, we usually have some alphabet, and some examples of functions could be f, g, or a very concrete function, the plus. We don't know yet how plus is defined, but that's a function, right? It takes usually one thing on the left, one thing on the right, and it returns a new value. So that's a function. Then predicate symbols, there are some very simple predicate symbols like true and false. They don't have any parameters. We cannot put more stuff in them. We can't like have true of some x or y. It's just basically like a constant. And we also have an alphabet for these predicates, because we need to distinguish what's a function, what's a predicate. And then a very important thing is the arity of a function. That's basically how many parameters can it take. So if we have arity 0, this means it can't take any parameters, then it's a constant, right? Because there's nothing that it takes as input, so it can only be a constant. So true, false, these would be constants. Then the notation here used on these slides, if you're not sure about the arity, you can put this like / and then the number of the arity. So f with this /2 would mean that it has arity 2. So it can take 2 parameters and then return some value. And then we have a set of variables, and these variables are not in any of our functions or predicates, right? So you can use a variable, but you can't use a function name for a variable name. This would clash like in any programming language. You have those keywords, and you can't put your or you shouldn't have your variables as the keywords, for example. Here, the clash is between the function symbols and the predicate symbols. And then we can have a set of variables. Now let's look at some examples to understand this arity of functions, or the arity of our symbols. So there are some statements about arities, and you should select all the correct ones, all the meaningful arities. So it says here the number 12 has arity 0, or the number 1 has arity 1. And remember, arity was this, like, how many parameters does it take in our framework. Okay, so we have some answers. So the number 12 has arity 0. Why is that? That's correct. Why? it's a constant. Yes, exactly. It doesn't have any parameters, so yeah, it has arity 0. The number 1 has arity 1? No, because it's a constant as well, so it also has arity 0. Then the addition function has arity 2, the plus. Yes, we can take 2 parameters on the left, on the right, so arity 2. Yeah. The negation function has arity 2? No, because it has arity 1, right? We can negate 1 parameter. Then the relation whether one person is richer than another person has arity 2? Yes, because it relates 2 people. If you give it 2 people and it says yes, one is richer than the other, or no, one is not richer than, or the first is not richer than the second. Okay, yeah, so that's about arities. Now, the next thing we have is terms. And the set of terms is some set formed by these syntax rules. So a term is either some variable, or it's a function applied to other terms. So yeah, very simple, and it only works for these functions in F. So terms, we wouldn't have any predicates in there, right? A term would only be either a variable or function applied to variables. Now, well, it says function applied to terms. Does it mean I can nest functions? I can apply a function to a function? Yes, exactly. Because I can, well, a function itself is a term, so I can plug it in as a term inside another function. So I can basically nest functions. I can put variables in functions or just have variables themselves. Okay. And then we can also say a term is ground if it contains no variables. And now let's have a look at, we don't have an example for terms. Okay, but terms are very, very simple, right? Variables or functions applied to variables. Or ground terms, how can we have no variables in a ground term?
It's a constant.
If it's a constant, yeah. So if we have a function that's a constant, then it's a ground term because we don't have any parameters of it. Or if we have a function on constants, right, then it's also fine. Okay, so there are probably many ground terms that we can create. So yeah, if we would have, I don't know, 1 plus 1, would that be a ground term? Yes, because 1 is a constant. Yeah, and plus is a function, so that's a ground term because we don't have any variables. But if we would have x plus 1, then x would probably be the variable. So yeah, this would not be a ground term. Okay, then yeah, atomic formulas. In our language, an atom would be defined as some predicate over terms. And yeah, we can say an atom is again ground if it contains no variables. So again, the same thing. If it doesn't contain variables, then it's ground. And then we can say literals are atoms and the negation of atoms. Okay, so just wrap some kind of predicate around some terms, and then you have your atomic formulas. Now, to build quantifier-free formulas, then we can take atoms and add our Boolean logic operators, because now why can we apply negation to an atom? Because an atom is always wrapped in a predicate, and a predicate is true or false, right? That's how we can apply these operators here, which are defined for our propositional logic. We can apply them to these new atoms because now we can basically, our atoms have a Boolean value after the evaluation of the predicates. So yeah, we have again negation, B implication, conjunction, disjunction, and regular implication. And again, you could just use the negation and disjunction to abbreviate all the others. But yeah, here they all are. And then basically the highest level of elements that we can express in our logic are first order logic formulas or first order formulas, and we can add some quantifiers, and then we get first order formulas. So that's basically on top of our formulas that we had so far, our quantifier free formulas, we can wrap them in quantifiers, and then we have the complete language of our first order formulas. So we have the for all, which is the universal quantification, and the exists, which is the existential quantification. And then there's something called free occurrences of variables. Are those where the variables are not bound by a quantifier. So what does a quantifier look like? A quantifier always has some kind of variable that it quantifies over. And then this formula here, if it's not a ground term, then it can have many variables, right? But if it has, for example, the variable x in here, in this formula, then this means that x will have the value that we used in this quantification here. So x is then bound to this x. But if there are two variables in there, for example, x and y, and we only bind x, then y is still a free variable. So it has, yeah, it occurs freely inside the formula. So let's have a look at some examples. We have this formula up here. For all x, for all y, x and z implies y. I'm not asking you to evaluate it. I just want to know which ones are the free variables in this formula. So we can look at, well, how many variables do we have? X, y, and z. So yeah, choose which ones are occurring free in this formula. So does x occur freely? No, because it's in a quantifier. So here we have for all x. This means that x is not a free variable. Here we have for all y. So y is also not a free variable. So the only free variable is z. Then let's have a look at the next one. What about this formula? Now that's a bit tricky. For all x, x equals y, or for all y, x and z implies y. So now the question is, which binds stronger? Did we say which binds stronger? No, we didn't have the operator precedence, did we? Let me check. Do I have it on this? No. Okay. So let's put some parentheses. Now I'm presentation mode. I can't easily edit it. So imagine some parentheses here, and well, some parentheses around this other one as well. Sorry? Yeah, so then what would be the free variables? Where is y free? Y is free in this one, right? And here, y is bound. Is x free in this one? X is free in this one, right? We only quantify over y. Like, if we had these, well, I really should put the parentheses to make it more clear. So if we have this for all x this and or for all y that, so if the highlighted thing was again in parentheses, then we would have the occurrence of x free and z free. And this means that we actually have kind of twice the variable x because we have it once bound here, but this name only relates to the left part, and then we have the variable x here, which is now free in this formula. So it's basically another variable x. You can kind of like in loops, when you nest variables, you can have a local variable which has the name of some higher visible variable, and it kind of shadows it. So now, like in a method, you can define a variable which actually is a field available in that class, and then it will take the locally known name as the one that it uses. So that's exactly the same here. If we have this scope of the for all that goes from this for this x, then it will take this locally known x here, which is bound by this quantifier, and here it will take some free x because it's not bound by the second quantifier. Okay. Yeah. Then we can recall a sentence as a first order formula with no free variables. Okay, but yeah. We will see that the more interesting ones are ones with free variables, because then we might want to check what values we can assign to those free variables to make a formula satisfiable. So yeah. But now we have this kind of syntax, right? We can now write formulas. So we write our quantifier-free formulas, and now we extended them with quantifiers, right? So now you can all write first-order formulas. But do you know what they mean? We have to give them a meaning. So to give them a meaning, that's called the semantics. Now for propositional logic, the semantics was really easy because it's either true or false, and we know what with the truth tables, we basically said what the semantics are, right? We said and means that both of them have to be true, and so on. So there the semantics are quite easy. But now for first order logic, we actually have different parts that we can have in our formula. We can have those predicates, we can have the functions, we can have variables. So how do we give this thing a meaning? How do we make sure that we can evaluate the formulas? For that, we need some domain, which is often also called the universe. So it's some set of elements. And these elements are, yeah, maybe some values that we can assign. So the easiest thing is assignments to variables. So this xm, that's in our model. So to give the meaning, we need models. And our model interprets variables by assigning them concrete values. So the variable x, we might assign a concrete value from s. So now what might s be? This is something we have to say when we give this model. The model has to define this. The model has to define what is s. So for example, for the cats, dogs, mouse thing, we would probably take a model where s is the set of integers. So s would be then the set of integers. Then our variables, dog, cat, mouse, we would each one assign a specific integer. Then we need to interpret also our functions. So we would have to say, what actually does plus do? And yeah, we probably define it in the way that we know what plus does, right? If you have one thing on the left and one thing on the right, it adds them up, right? It gives the sum. But that's not yet defined. We have to define this by giving a concrete function that interprets this plus symbol on the domain of integers, right? So on this domain that we gave. So we would then have a function that, for example, takes n parameters. So plus, we said arity is 2, so it takes 2 parameters and gives us a third value. So it could take 1 and 2 as the parameters, and it will give us 3 as the result. But that's something the model has to give us. So this interpretation, that's something the model would give us. If it's not from somewhere else, we will see that there are, for plus standard things, we can get them basically bought in from somewhere else. But in general, that's the semantics. We have to get interpretations. Similarly, for predicates, the predicate hates. Now, for this Agatha puzzle, what would be the domain S. We said the predicates, we have a predicate hates, we have a predicate killed, we have a predicate richer. But what would be our domain S for this Agatha puzzle?
3 people.
3 people, yeah. We would probably have a set of 3 people. So the domain S would be Agatha, Butler, and Charles, right? And then each predicate, so for example, the predicate richer would relate always tuples of people. It has arity 2, so it relates maybe Agatha and the Butler, or Agatha and Charles, right? So that's how we would have to give, the model will have to give interpretations. The model will have to say, how does this predicate work? When is this predicate true? When is this predicate false? And it does so by relating the elements from the domain. Yeah, so we basically give interpretations for functions, for predicates, and assignments for variables. And the very important thing is this set S, right? Because that has to come from somewhere. And we saw that although it's the same first order logic, the models are completely different, right? Even like in terms of the structure. The model for the Dreadberry Mansion puzzle, we had the domain as 3 people. For the dogs, cats, and mice puzzle, we had the domain as integers. So yeah, and all that is in this first order logic. Okay, so a formula is true if in some model, so let's say we have a formula and we have a model. The formula is true in that model if it evaluates to true under the given interpretations over the domain S. So basically, we apply all these interpretations. We replace all those funny symbols by their correct interpretations on this one domain that we have, and then we check is it true or false, right? And M is a model for some set of sentences. T, if all sentences of T are true in M. So you can also define a model for a set of sentences which were those quantifier free. No, not quantifier free. These were the ones without free variables. So if everything is completely determined in terms of the variables, then our model can be checked against the different sentences. So yeah, sentences, they could also then be the different constraints that we want to hold. So yeah. And then of course we want this model to satisfy those constraints. Good. So now let's look at the semantics of some terms. So a term in a model is interpreted as, for each variable, we basically interpret it as the assignment of the variable, right? So this xm, this x in the model was some concrete value assignment. But what do we do with functions? Well, functions, they are interpreted by replacing all the terms by the current interpretations of the term. So it's like a recursive thing. If I want to translate a function that is over terms, I have to translate all the terms, and I have to replace the function by its interpretation in the model. So this, I don't know, plus, I have to say, well, that's actually the function that adds the 2 numbers. Okay, then the predicate is true if and only if now it's terms, so we're still on the kind of syntactic level, we replace them with their current interpretation of the term that's given to us by the model, and then we check whether it is in this concrete predicate that the model defined. So this interpretation of the predicate that was now some subset of value combinations. So if we would have something like the richer predicate and we have Agatha and the Butler, then we would have to first go ahead and replace Agatha by actually the Agatha element from the domain S, and the Butler by the Butler element from the domain S. And then we have to check whether they are related in this interpretation of the richer predicate. So that sounds a bit strange because now we have like on the syntactic level, on the term level, we have an Agatha, and we have an Agatha in the semantics level in this domain S. Often we can give them, let's say, the same name, we can give them the same symbol, but yeah, in theory they are actually different. But we don't have to worry about that too much. We just have to know that there needs to be something like this model, and that this model has lots of responsibility because it has to say what's the domain and how do we interpret each of those functions. And if we want to, here we said that if we want to a model for a set of sentences, so we want a model for a set of constraints, then that's what we will ask the SMT solver to do. So the SMT solver has to come up with all these things. It has to give us interpretations and meanings for the domain, the functions, the predicates. So an SMT solver has to do a lot more than a SAT solver, right? Okay. Yeah, some examples of the basic semantics. We can define the semantics. That's basically our highest level formulas that we can build. So a formula is true in some model if the model, so the negation of a formula would be modeled by M if the formula itself is not modeled by M. That's the simple interpretation of negation. And the equivalence, or here the B by implication, would be modeled by this model if they are both modeled by the model. And then for the other ones, it's simply, this operator here is only, so the conjunction here is only modeled by our model if our model models both of them individually. So for or, then of course it's enough if one of them is modeled, and so on. The tricky bit is then the quantification. That's the new part. So for all x, this formula should hold. This means now we have to take the model and replace the occurrence of x by some specific value. And we have to do this for all the values from the domain. So it says for all of them, right? So if we have some variable in our formula and it's inside a universal quantification, then we basically have to check for all the possible variables if we replace x by, for all the possible values in the domain, if we replace x by that value, does the model still model the formula? So that's for all. And for exists, we're just asking, is there some value that we can replace the x with, and then do we get that the model now models the formula. Okay. That's this variable assignment. So we update the model by saying this variable x now needs to point to this specific value s. Okay. Then we can see that propositional logic is actually included in. So the SAT solving stuff that we had so far with propositional logic, it's some subset of first order logic. We don't have predicates. We don't really have functions except for constants. And then we just have kind of these operators. The quantification we don't even need. So we can build everything that we had in our propositional logic. We can build in first order logic, right? And lots of the stuff that first order logic has on top, we don't need. And then this interpretation here, there are no variables, so everything should be quite simple. So we can just interpret a formula then, again, simply based on these rules, and see if we get true or false, whether it's really modeled by, and that's our that's our semantics of propositional logic. So what we have is truly more than what we had before. Okay, and of course then the domain would usually be this true and false, and the constant true we map to the value true, and the constant false we map to the value false. And now we would have to assign these variables to some values in S. So to satisfy this, to make it true, we could, for example, set P false, Q false, and R false. Then we have false implies, and yeah, we don't need to go on because that's already satisfied. Okay. Now, if we look back at this thing, we see that this was actually already first order logic. And now we know what these elements all mean. We have some predicate symbols. We have some variables, x and y. And we have some constants. Here, this A was standing for Agatha. And that's our constant Agatha, B for Butler, and C for Charles. So those were our constants. Then we have these predicates here, killed, hates, richer. And those are our constraints on those symbols that we have introduced. Now, what would it look like if we want a model for this? We need a domain, right? I mean, you already mentioned it, right? The domain would have to have some values, right? So it would be those three values of the Agatha, Butler, Charles. Then, of course, the interpretation of the variable or of the constant A should be this Agatha from that set. C should, of course, map to that set in our domain. So now this A is different from that A because this A is the constant in our formula, and this A is the value in the domain that our model provides, right? And richer could be mapped, for example, to this predicate that only relates B and A, which would mean that only the butler is richer than Agatha. But that's not necessarily conforming to all those constraints. So these are just examples. And of course, what we wanted to figure out is what element, what value might there be in this interpretation of killed, where A is on the right side. So who killed Agatha? That was the original question. So the question mark is what do we need to do to find that concrete assignment? So here, this is not a complete model because we have these kind of incomplete things in there, right? So or it's not a model that would model our formula. Okay. Now that we have all these building blocks, there's actually some additional stuff that we need because we don't want to always define what do these functions mean. We want to have like some kind of library of existing functions, of stuff that we know, stuff that we want to reuse. Right now, we said, well, equality is some kind of predicate, but how is that defined? We would have to define it each time we want to give a model, right? And ideally, we would hope that everybody defines equality the same way, right? But how can we be sure if everybody can define equality from scratch in their model? This would be very confusing if we define different kinds of equality and then they might even contradict, right? So we don't want that. So the trick that we can do is we can add some theories. The theories, what we will see is they will basically they always work over some signature. So the signature is the stuff that has the function names, that has the predicate names, and it's a set of sentences or axioms. So it's a set of things that has to hold over our over our signatures. So a set of properties that our signatures need to have. And what we capture is the intended interpretation of the functions and predicates in the signature. So we have usually plus, we want this to be addition. We don't want plus to be anything else. So that's our intended interpretation of plus. And to capture what does plus mean, we can put that into a theory, or that this 0 thing is actually the number 0. These are things that we need to put in theories, because so far in this first order logic, nobody ever said anything like that. We just had those predicate names and we had the function names, but we never gave them any meaning. So we want some fixed meaning, and that's why we add some theories. So you could also say that the theory, you can view some kind of first order theory as the class of all models, because, well, because all the models that conform to this theory have in common, let's say, the way they interpret addition. And they all have in common that the values in the domain are some numbers, right? Otherwise, you couldn't really give interpretations. So a theory then gives you kind of a huge set of different models, because all you require from the models is that all these models, if they belong to one theory, they must satisfy the axioms of the theory. And we will look at some examples. So, for example, equality. That's already a non-trivial theory. How can this be? Equality is so easy, right? It means the thing on the left and right side is the same. But it's not that easy. And that's not because of satisfiability modular theory. This complexity is not related to the tools that we're going to use. It's just that inherently, mathematically, to define what does equality mean, you need this stuff. Or that's what, let's say, the world has agreed on. This is what equality means. So, for example, the world has agreed that equality means that we have reflexivity, so that an element is equal to itself. That's this reflexivity. If you find an element, it must be, or, well, actually all elements. All elements, they must be equal to themselves. Then we have symmetry. So if x is equal to y, then y also needs to be equal to x. That's not a given, right? If if equals is just some kind of predicate, like hates, then hates doesn't have to have symmetry, right? Nobody requires that, but for equality, we do require this. So for equality, we require that if x is equal to y, then y is also equal to x, no matter what x and y are, right? For all possible things that x and y could be. Then transitivity, so if we have x equals y and y equals z, then also x must be equal to z, right? So if the first is equal to the second, and the second is actually the same as the third, then the first and the third also must be the same. Otherwise, there's something wrong with equality, right? Any property missing? Or is this all you expect to have from equality? Who was thinking that equality is even simpler than this? What if we define equality as some relation, then we want all these things to hold, and actually there's slightly more. If we relate further, for example, functions, then we also want that if I have a function and I call this function on a set of variables, and my variables, my x's, are the same as the y's. So basically, I feed the same function the same values, then I want the function to return the same result, right? So if I say x is 1, and I want to evaluate 1 plus, well, sorry, I want to evaluate x plus 1, then I get 2, right? And if I say y is equal to 1, and I want to evaluate y plus 1, I should also get 2. I shouldn't get a different value, right? So, and that's exactly what it says here. If the x and the y are the same, then the function called on the x and the function called and the same function called on the y must also be the same. And that's then congruence. And then finally, we have another axiom called equivalence. So for all, again, variables x and y, if they are the same, and I evaluate a predicate on them, then this also has to give the same Boolean value. So this is now like the if and only if. That's basically if the same predicate is called on the same values, because these variables evaluate to the same values, then the predicates have to also give me the same result again. Okay, so that's equivalence. Now we have, I think these 5 axioms, they finally give us the theory of equality. And now we can work with equality the way we used to work with it, right? Sometimes you write things on the left, sometimes you write them on the right, and you're expecting that it's still the same, right? So same meaning. So that's the symmetry. Now, yeah, go ahead, use your symmetry. It's now fixed as axioms, and you can rely on it. So let's have a look at some examples. So all these rules, they're not really anything. Sorry, that's piano arithmetic. How come? I think the example is missing. Yeah, let's skip this for now, because I think this one. Yeah, this is the next. Actually, it's I'm missing the example. So let's. Yeah, there are no equality examples here. So yeah, that was the theory of equality. So this is all stuff you all knew in the back of your head, in the back of your mind. You all knew these, right? They're not new. Now something else, piano arithmetic. So that's some very simple form of arithmetic where you have the constants 0, 1. You have plus and multiplication and equality. This is based on taking all the axioms that we had before. So we take our equality now as a theory. We say we're kind of taking all of these axioms that we had before, and we have additional axioms. So we have a 0 kind of definition. So for all x plus 1 equals 0 is not possible. So this basically means that you cannot get to 0 by using addition in this theory here. So there's basically you have 0 and you have addition, but you can never get back to 0 by adding 1 to anything, because we don't have negative numbers here, right? So yeah, this is the definition of 0. Then we have a definition of the successor. So x plus 1, if that equals y plus 1, then we have x equals y. And so basically the successor, no matter what the value on the left is, the successor always gives us the unique next thing. It doesn't give us, if the variable is, I don't know, x equals 5 or x equals 6, it never gives us the same value then. If this gives the same value, it means that the two variables had the same value. Yeah, then we have some further axioms for doing induction. We have that 0 is basically the neutral element. So if we have x plus 0, we end up with x. And we have, well, the successor of the plus that we can, if we have x plus and then the successor of something, it's the same as doing the addition first and then taking the successor function. So these are some some rules that you might have had in some early proofs in school. We use that, and we have like multiplication with 0 always is 0. And then, of course, we need to define what multiplication means. And you can define multiplication by saying, well, x times the successor of y is x times y plus x. So yeah. And then you basically reduce 1 from the y until you end up with 0 and this long addition there. So multiplication is defined as, well, a bunch of additions. But that's only as an axiom, right? This is only some law that our multiplication has to satisfy. So how we actually do multiplication, whether we actually do it with addition or not, that doesn't matter. It just has to satisfy this law, right? So that's all. And yeah, so that's giving us some very simple stuff. Is this already enough for our cats and dogs and mouse puzzle? So we had, well, of course, equality, right? Then we had something like 100. We should buy 100. How do we do 100 in piano arithmetic? We don't really have other numbers, right? We only have 0 and 1. So basically, this is this really annoying arithmetic where you have to write the, let's say, 2. You have to write 2 as 1 plus 1. You have to write 3 as 1 plus 1 plus 1. So this is like the successor function. So 100 you would have to write as, well, 1 plus 1 plus 1, and this thing, well, like 100 times. Okay, but then we can basically, we have multiplication, we have addition. The only thing we had was this like greater or equal, right? We said we had this kind of inequality. So we will probably have some additional theory of inequality, but then we could represent with this arithmetic. We didn't do any division, right? No, I don't think so. So yeah, so with this thing, we could already represent our dogs, cats, and mouse puzzle. That's great. So we managed the Agatha thing. We managed the cats, dogs, mouse puzzle. We had this one with the emojis where we had like formulas over emojis. This had division, right? So we might have to have another theory for that. But you can imagine how this goes. There are more theories, and we're not going to go over all of them because there are tons of them. And there are basically libraries where you can look at what theories exist. There are many built-in theories in the tools that we will use. And everything should be fine to solve our puzzles. But now it says here, piano arithmetic is undecidable. What does that mean? Anybody got a clue? Is that good? Is that bad? What does undecidable mean? Sorry?
Cannot decide the outcome.
We cannot decide the outcome. So here, the kind of the problem would be maybe given some formula, find the model, or given some formula in the model, is it, so I think here the solution would be, can we find a model for some formula, and it's undecidable. So there is no algorithm which can do it for all cases. There are cases where an algorithm can do it, otherwise we would be doomed, right? But there are some cases where an algorithm or any algorithm would fail to produce a solution. So, but now let's not, let's not skip ahead. Let's look at first some simple examples. But this requires all the axioms. Sorry? They're all true? Some people already answered. Okay, so x plus 1 equals y plus 1 implies x equals y. This was sorry, which one? Successor. Yeah, okay, so that was directly an axiom. Of course, then trivially, yes, it's true. X plus 1 equals y implies y is not 0. that was the 0 thing and the equality with y, right? So we had to kind of mix. Yeah. Then x plus 1 times 0 equals 0. That's here the times 0, and our x was a bit more, well, this is for all x, right? So our x plus 1, of course, then it's also for x plus 1. Okay, and the last one here, that's also the extraction of the times, but we have 2 times the successor, so we basically have to apply this axiom twice if we want to solve it like that. Okay, yeah, so all of them were true. Exactly, good. And then, of course, now we are interested in satisfiability, and now we're interested in satisfiability given a theory, right? So we have this theory of piano arithmetic, we have this theory of equality. So now we should relate this to satisfiability. So the way we can relate this is we say some formula is T satisfiable in this theory T if there is a model for the theory. So the model must respect all the axioms we gave in the theory, where our formula evaluates to true. So now if we want to say that this holds in this theory T, we could write the T as a subscript of these models, because there might be different models and not all the models might satisfy the theory axioms. And of course, if we have a specific theory in mind, like the equality, we would always be interested only in models that actually satisfy the equality as we know it. If there's some model and it redefines equality, then we're not really interested in this, right? So we're usually interested in some T satisfiability for some chosen theories that we are using. And we will see that in all those cases that we're dealing with, the theories, they can be automatically chosen. So basically, the tool that we will use, it will choose the right theories for us automatically because there's not really a clash on the theories that we use. So if there's something about arithmetic, it will choose the right arithmetic for us. And we don't need to even care about which theory to say we want to use. It will use the appropriate ones for us. But there are some where we might want to import additional theories, but yeah, not in this lecture. Okay, so and then of course there's also validity with respect to some theory. So we can say that some formula is T valid in some theory T if for all the assignments to the variables, to the free variables of the formula, this formula is in the theory. So yeah, it evaluates the true for every model of the theory. So no matter what assignment our model gives to the to the free variables, it would evaluate to true. So and then that would be T validity, and we could write it without this model because it's basically for any model conforming to the theory. Okay. Now let's have a look at some first order logic with theory of equality. I have to look the other one. So now if we want to select all the equalities determined by the theory of equality for these variables x, y, functions f, g, and predicates p and q. Maybe that's the question that should have been there earlier, right? I think that's just something wrong with the order. So I'll go back to the, probably need these axioms here, right? Okay. Okay, so let's have a look. The first one, that's determined by the theory of equality, and that's the reflexivity, right? So reflexivity gives the answer to the first one. What about the second one? It's not determined by the theory of equality. Why not? Well, we see here the parameters. Here's an x and there's a y, and we don't have any further information, right? We don't know how x and y relate, so the theory of equality doesn't determine anything here. We don't have an axiom that tells us you can combine these axioms and you know it. What about this one? F of xx equals f of xx. And which axiom tells us? The congruence, because that congruence says if we call it on the on variables which have the same value, well, here we even have the same name, right? But still, it's the congruence axiom which tells us, yeah, this one is this one is true. What about this one? False, because the congruence requires that it's the same f, right? It's the same function. So we don't know how g and f are related, so we don't know. There might be models where this is true, but then it's not determined by the theory. Then it would be determined by the model. Okay, then these ones here, that a predicate of x equals the predicate of y for x equals y. That's basically the equivalence relation here, or equivalence axiom here. Yeah, for because we have this x equals y, and then they are equivalent. Okay, good. So now, what about satisfiable formulas in first order logic with the theory of equality? So what does this now mean? This means that if we have some model, this model has to conform to all the axioms of equality, so it can't really break them. Otherwise, it might be too easy, right? Otherwise, if you say your equality could be arbitrarily defined, then you can maybe always find a model that satisfies them. But now this model has to give us a real equality as we know it, right? So, okay, so what about the first one, x equals true? The model can simply give a value that it can, the constant true can be mapped to the value true in the domain, and x can be interpreted, x is a variable, so x can be also interpreted as the value true, right? So that's clearly something satisfiable. We can give easily some model that satisfies that, right? What about the second one? For all x, there exists a y such that x equals y. So now we have this, yeah, what do we have? Do we have any thing that we can use, any axiom that we need to rely on? Well, I mean, reflexivity might be a good axiom to rely on, that if we put the same element on the left and on the right, it's giving us the same thing. Now, the question is the same element, can the same element be picked? So we have to, the for all says it picks some value for, well, the for all has to go over all values of the domain, right? So if these are integers, let's say it starts with, I don't know, 1, then x equals 1. Okay, now, does there exist a y, so some value from our domain that makes x equal y? Yeah, so if we can assign also 1 here, right? Because we just have to find a single one. So then 1 equals 1, fine. Now, the for all says, but you have to check all values. So let's say x equals 2. Can we find a value that is equal to 2? Yes, of course, 2 is equal to 2. So yeah, this thing works fine. So this one should also be true, like, yeah, the majority said. Okay, then there exists an x such that for all y, x is not y. Why can we not find this? Why would that be true? Sorry, why would that be false?
So yeah, for certain values it will be true. Let's say x is 1 and y is 1.
But here, these things actually say we have to do it for all values, right? The for all quantifier, x and y are not free variables, so we can't really arbitrarily choose. They have to go through all values of the domain. And no matter what domain we choose with equality, this means that let's say we pick one value, and then we have to pick each possible value again. So we have to pick also the value that we previously picked, right? Because we have to pick all the values in the domain. So this means that we will, if we pick tier 1, we have to pick 1 here at some point. If we pick tier 5, we have to pick 5 here at some point. And then there's no way that 5 does not equal 5 because of the reflexivity. Okay, so the last one is not satisfiable. Of course, if we didn't have the quantifiers, then it was easily satisfiable, because then the model could just give some assignment of x and some assignment of y so that they're not the same, right? So then we could assign x1 and y5. Okay. Yeah. Yeah. So much about equality. We had arithmetic already. We had satisfiability, validity, and yeah. Next session we will continue with this issue of undecidability, what it actually means. But yeah, this will be next week, and then yeah, we will get there and see what the limitations are. Yeah. So see you next week.